Welcome back. In this video, we're going to be implementing circuits from Boolean expressions. And basically that means we're going to be given an expression, and like an output expression, and we're going to discuss how do we generate a circuit to be able to implement that expression. The other thing we're going to discuss today in this video is how to describe the truth table, the symbol, and the expression for Nand and NOR gates. Up until now, you've studied the AND, the OR, and the NOT gate. And those are the three most basic foundational gates, but there are a lot of other gates and logic functions that stem from the AND, the OR, and the NOT. And today we're going to learn about the NAND and the NOR, which are based on some of the ideas from AND, OR, and NOT. But first we're going to begin by implementing circuits from Boolean expressions. So, for example, let's say that you were given an expression and you were told to create a circuit based off of that expression. The question is, well, how do we do this? How do we approach that idea? For example, we have the expression here on the screen, y equals a and c, or b and not c, or not a and b and c. So what's our circuit going to look like that's going to produce this expression? The idea here is to figure out how we can deconstruct this expression into a circuit that will give us an output that matches. So just by looking at the expression, we should be able to use what we've learned about and, or, and not to deconstruct this. For example, we've already talked about how multiplication is the symbol we use to represent and. We've talked about the plus sign is the symbol that we use to represent or. And we've talked about the over bar is the symbol that we use to represent not. So looking at this expression, we have to use those concepts to understand what kind of circuit would we need to build to implement this idea. I can see that C and A are both inverted, so I know I'm going to need some inverters at some point. I can see that A and C have to be going into an AND gate. B and not C have to be going into an AND gate. And then not A and B and C need to be going into another AND gate. And then all of these things are ORed together. So all of these things have to be going through an OR gate. So let's take a look at how this would work. Here's our expression. And first off, you need to identify how many inputs do you have. In this case, there are 3 inputs. So you know you're going to have to start by illustrating those 3 inputs. Then we'll begin by attacking the first piece, the y equals a and c. That tells me that a and c have to be going through an AND gate. And that's what that would look like, where C is connected right down here, A is connected right here, and there's my AND gate. The next piece I would need is the B and not C. So in order to implement that, I need 2 things. I need an inverter to invert C, and then I need to take the output of that inverter into an AND gate with input B. This piece would implement this small section of the expression. Next, we need not A and B and C going into an AND gate. So I'm going to need an inverter for A. And then I'm going to need an AND gate. And remember, AND gates can have more than 2 inputs. In this case, we can draw the AND gate with 3 inputs. And it'll operate in the same manner as a 2-input AND gate. So the output of this AND gate will only be high whenever all 3 inputs are high. And this piece here would give you this piece of the expression here. But now we have to tie it all together. I can see that this goes into an OR gate with this, which goes into an OR gate with this. So we need to add that to our circuit diagram. So when we combine it all together, we can use a 3-input OR gate to illustrate the expression. Whenever you're drawing a circuit to implement a Boolean expression, you just want to make sure that you can trace the expression from each gate back to your final output that you started with. So when you draw your circuit, you should write the expression of each gate, just like we did in the video prior to this one when we were describing circuits and evaluating circuits. You want to write the expression for each gate, write the expression for your output, and make sure the expression for your output matches what you started with. If so, you've then drawn a circuit that will implement a Boolean expression. So I can build this circuit, and I know that the output will be basically described as A and C, or B and not C, or not A and B and C. So that's the circuit that you would want to construct to implement that expression. So let's try another one. What I want you to do is pause the video and try to draw the circuit to implement x equals the quantity A or B and the quantity not B or C. Keep in mind you have some parentheses here. You have to remember order of operations. Think about what might come first, second, third, etc. Think about what kind of gates you might need. And then draw the truth table to represent the output of this circuit. So take a minute, hit pause, try this example on your own, try to construct a circuit and a truth table to implement that expression. All right, let's take a look at the answer to this one. So I have three inputs, A, B, and C. So I know I'm going to have to start my diagram with three inputs as well, A, B, and C. Next, I'm going to start with the first piece, A or B. So I'm going to need an OR gate for the first piece. The second piece is going to be the not B or C. So I'm going to need an inverter as well as an OR gate to construct this piece of the expression. Lastly, I can see these two groups of things are being ANDed together because of the multiplication that's implied. So I'm going to need an AND gate to tie these two things together in order to create the expression. So this circuit is what I would actually build if I wanted to implement this expression on my breadboard. If I actually were going to be building the circuit, the only way that I would be able to test it and know that I built it correctly is by using the truth table. So you have to know how to create the truth table by hand and then use it to test your circuit later on. So next we're going to draw the truth table for this circuit. If you have three inputs, that means you have to have 2 to the third, which is 8 rows in your table. So I have one column per input, input A, input B, input C, and here are my 8 rows set up using the techniques that we discussed previously in the last video. And then I have one column per gate. One column for the OR gate, one column for the inverter, one column for the second OR gate, and then the final output, which is this expression right here. So first I'm going to do A or B. So I'm going to look for the times when either A is high or B is high and put a 1. I can see that B is high in these two places, A is high in all 4 of these rows, and in the last 2 they're both high. So this is what my expression is going to be for that first OR gate, A or B. Here's the output. Next I have the output of the inverter. Well, that should be column B inverted. So I'm going to take every 0 and make it a 1, every 1 and make it a 0. Next, I'm going to take not B and C and put them through an OR gate. So the two columns that I have to make sure I'm looking at is this column, and I'm going to be applying the idea of OR. So this is what I'll get. I can see that B is high in these 2 places and in these 2 places. I can see that C is high here and here and here and here. Remember, with an OR gate, as long as at least one input is high, the output will be high. So I'm looking for all the places where either B or C is high and writing a 1. If they're both low, I'm going to write a 0. For example, right here, both inputs are low, so the output is low. Lastly, I have to take this column and this column and perform the AND operation. Based off of my expression and my circuit. So that's what I'm going to do next. So I'm only going to be writing a 1 at the places where both of those columns are 1. So as you go through, you can see 0 and 1, that's a 0, 0 and 1, that's a 0, 1 and 0. That's a 0. Then we have 1 and 1. There's your first one. 1 and 1. There's your next one. 1 and 1. That output is also 1, and so forth. And that's how we'll get the truth table. So now that I have a circuit to implement my expression, the next logical step might be to go build that circuit. Once I build that circuit, I'll test that circuit, and I'll make sure that every single input produces the output described in the truth table. Every time the output says it should be 0, my circuit should reflect that. Every time the output says it should be 1, my circuit should reflect that. And if it doesn't, I know that I have to go do some troubleshooting to figure out why. Turn to the next example in your notes. It says draw a circuit to implement y equals, and then we have 3 quantities, not A and B and not C, or not B and C, or A and not C, and then draw its truth table. So once again, hit pause, try to draw this circuit yourself. You get the most benefit out of doing the problems yourself first and then checking to see if you're right. So take a minute, hit pause, try to draw the circuit yourself, try to draw the truth table yourself, and then check back in for the solution. Here's the solution for this problem. Here's what your circuit should look like. And we're going to start looking at this piece by piece. If I look at the first piece here, I have not A and B and not C. That means that A and C both have to go through an inverter. So we can see that A goes through an inverter here and becomes inverted here. We can see that C goes through an inverter here and goes in right there. And then input B is not inverted. So this first 3-input AND gate will take care of the first piece of our equation. Next, we have not B and C. So going into this AND gate, we have not B. So B comes down here, gets inverted, goes to the AND gate, along with C. And then lastly, we have A and not C. So notice that I can take the output of this inverter right here, which gives me not C, and I can create a node right there, and I can bring that node down here for not C. I don't need another inverter. I've already inverted C once. I don't have to do it again. I can simply create a node at the output of this inverter and transfer not C down here. So the output of this OR gate will be the combination of this input and this input. So I have the output of this OR gate is not A and B and not C, or not B and C. And then I have a second OR gate which takes this expression and combines it with this one using OR to give me my final output. Now, if you're wondering why did I use 2 OR gates to implement that, that's because in the real world, you may not always have access to a 3-input OR gate. A 3-input OR gate would work in theory. But for example, in our lab here at Valencia, we don't have 3-input OR gates that you can use on the breadboard. If you don't have a 3-input OR gate or a 3-input AND gate, you'd have to go and create one using what you have available to you. And what we have available are 2-input OR gates. So this right here is how I create the concept of a 3-input OR gate using 2-input OR gates instead. If you look at the Boolean expression, it still works out to be the same expression as if you had a 3-input OR gate. So that's why I demonstrated it this way. This may be a technique you might have to use in a future lab, where you'll have to create a 3-input OR gate by using 2-input OR gates. And you can take this same idea and apply it to AND as well. If you needed to create a 3-input AND gate, instead of using one that was already available to you, you could apply the same idea that is shown here to do that. And there's our output expression. Next, we're going to do the truth table for this circuit shown previously. And once again, I have 3 inputs, so I'm going to have 8 rows. And then I'm going to have 1 column for the output of each gate. First, I'm going to invert A. I'm also going to invert C. And then I'm going to do the output for the expression not A and B and not C. That would be the output of the first AND gate at the top of our drawing. So in this case, I'm looking for all the places where not A, not C, and B are 1. That's the only time this column will have a high, because they're all going into the AND gate. There's only one time where not A and not C and B are all high, and it's right here in this row. At any other time, at least one input is low, so the output will be low. Next, I'm going to invert B. And then I'm going to do not B and C, going into the second AND gate on our drawing. So I'm looking for all of the instances where not B and C are both high. Or you can always go row by row. You could say 0 and 1 is 0. 1 and 1 is 1. 0 and 0 is 0. So you can go line by line, or you can look for the instances where you know there should be a 1 and then fill everything else in as zeros. It's your choice. Next, I'm going to do A and C prime. So I'm going to be looking at this column here and C prime, or C or not C, which is this column here. And I'm looking for all of the instances where they're both high. And there's only 2 times when that happens. Right here, A is high, C prime is high. And right here, A is high, not C is high. Those are the only 2 times that this AND gate will get a 1. Lastly, I have to do an OR. And now I'm doing an OR between 3 columns. This one, and this one. I have 3 columns. They're all being ORed together. So if any input in any one of these 3 columns is high, I'm going to get a high. So I can see that in this row, they're all 0, so the output is low. In this row, we have a 1 here, so the output is 1. In this row, we have a 1 here, so the output is 1. In this row, 0, 0, 0, so the output is low. And so forth. You would continue going through identifying the output based on the idea that it's OR with 3 inputs. And that's your final answer. Next, we're going to move on to discussing the NOR gate. The NOR gate operates like an OR gate followed by an inverter. At the top here, you'll see the symbol that we use to represent a NOR gate. It's an OR gate with a bubble on the end. Anytime you see a little circle or a bubble, it typically denotes inversion when it comes to digital circuits. It gives you the idea that whatever is coming out of this OR gate is immediately inverted. And this is the symbol that we use for NOR. In this example, NOR has 2 inputs, input A and input B. And then take a look at the expression for NOR. The expression for NOR has A and B underneath an overbar as one group. This is how we write the expression for NOR. It will never be an A with a short bar and then a plus sign and a B with a short bar. That will never be representative of NOR. That would be incorrect. So when we discuss NOR, we are not going to write this. That is incorrect. This expression says take A and invert it, take B and invert it, and then OR them together. This is not what's happening here. What's happening is that A and B are going into an OR gate first, and then they get inverted. So these 2 expressions are not equivalent, so we do not want to write that. So this is the expression for NOR. This is the symbol for NOR. This is what the symbol actually means, right down here. But when you draw it on your paper, you're going to draw it exactly like this. And then here's the truth table for NOR. Notice that we have two inputs, input A and input B. The first output shows you what the OR gate would give you. The second shows you what NOR would give you. Exact opposite of OR. So you can see here that the output of a NOR gate will only be high when all the inputs are low. When all the inputs are low. Otherwise, if any of the inputs are high, the output is low. Exact opposite of an OR. So think about how an OR gate works. A NOR gate will give you the exact opposite output that an OR gate will give you. So, using what we know about NOR, I now want you to try to draw a waveform for the output of this NOR gate given these two inputs. Remember, the output of a NOR will be high only when both inputs are low. So take a second, pause the video, and draw the waveform for the NOR gate. And here's the solution for that waveform. There's only two places where both inputs are low, right here and right here. Since this is a NOR gate, that's the only two times the output will be high. Again, we're operating off of the truth table for a NOR gate. So whenever you're solving these problems, if you have to stop and recreate that truth table on the side of your paper just to remember how that gate works, I highly recommend you do that. So that you have a clear picture of what's going on. So remember, with the NOR gate, the output is only high if both inputs are low. Again, I'll go back to that truth table here. This is the truth table we're using to create that waveform. So let's say that we had a 3-input NOR gate followed by an inverter. What would the output expression be for that? And I want you to start by drawing a picture of a 3-input NOR gate. Draw a picture of it, and then write the expression that comes out. So if you have a 3-input NOR gate, the expression coming at the output would be just like that. All 3 of those go in as a group. They all get a long overbar as a group. That's the expression that would be coming out of a 3-input NOR gate. Now, if it's followed by an inverter, here's what would happen. You now have something that's inverted becoming inverted again. Well, a double inversion basically cancels itself out. So if you were to have a NOR gate connected to an inverter, you basically have just recreated an OR gate because you're taking something that has been inverted and inverting it again, thereby canceling the inversion in the first place. So it's definitely inefficient because you don't need to use an OR gate followed by an inverter. All you really need in this scenario is an OR gate. But I show this example just to show that if you ever see double inversions do cancel. However, you have to remember that the bar has to be the same length. The bar has to be the same length. So if you have one overbar that's only over A and B, and the other bar that's over A, B, and C, that is not a double inversion, and you cannot cancel it. But in this case, if they are the exact same length, they cover the exact same variables, then you can consider that to be a double inversion, and it will cancel out. Next, we're going to move on to NAND gates. The NAND gate operates like an AND gate followed by an inverter. Very similar to NOR. So now with a NAND gate, this is now our symbol. Notice it's an AND gate with a bubble on the end, showing us the inversion. The representation of a NAND gate, it literally works as if there was an AND gate immediately followed by an inverter. And notice the expression. The expression is A and B with one bar over the whole group. Again, do not write the expression for NAND like this. That would be incorrect. That is not NAND. Again, this expression says take A and invert it, take B and invert it, and then send them through an AND gate afterwards. That's not what's happening. The inversion does not come first, it comes second. The AND comes first. And so we want to make sure that we write our expression that way to indicate what comes first. AND came before inversion. This expression says the inversion came first and then the AND came second. So make sure when you're writing your expression for a NAND gate, you have the whole group underneath the bar. Next, take a look at the truth table for NAND. This example has a 2-input NAND. So you have A and B going in. The first column shows you what would come out of an AND gate. The second column shows you what comes out of a NAND gate. So the output of a NAND gate is almost always high. The only time it'll be low is when all the inputs are high. That's the concept of NAND, the complete opposite of AND. So once again, there's your reminder. The output of NAND is always A and B with the overbar over the group, never two separate overbars. Take a look at the next example on your notes. Hit pause for a second and determine the output waveform of a NAND gate with the inputs given. If you need to draw the truth table on your paper to remember how the NAND gate works, that should help you to complete the waveform. And here's the solution to this problem, showing that the output is only low whenever both inputs are high, which happens here and here and here. Everywhere else, either one or both inputs are low. And with a NAND gate, if one input is low or if both inputs are low, the output is always high. Exact opposite of AND. Next, we're going to combine the idea of NAND and NOR to implement a logic circuit. So now we're tying all three things we've talked about in this video together into one single problem. We're going to implement a circuit using the expression given, and we can only implement the circuit with NAND and NOR. That's it. Nothing else. No AND, no inverters, no nothing. Only NAND and NOR. So after we draw that circuit, then we're going to determine the output level for the circuit if A, B, and C are 1 and D is 0. So first, take a look at the expression. You can only use NAND and NOR. So you have to figure out what pieces of this expression represent NAND and what represent NOR. Let's start with this right here. I see some parentheses. I see a group of things that are being inverted. This piece right here tells me that C is going into a NOR gate with D. I have C or D inverted. That means NOR. So I'm going to have C going into a NOR gate with D. Then I can see that this entire quantity is going to be ANDed with A and B and then inverted. So that tells me that the NAND gate will come next. Here's what the circuit would look like. C and D have to go into a NOR gate. So right here, I get the expression that I've highlighted up above. I get C NOR D. That's how we might say that, C NOR D. Now that goes into a NAND gate with A and with B. So what comes out is this and this and this with a big overbar over the whole group. So there's my circuit to implement this expression only using NAND and NOR. Lastly, we're going to determine the output level of the circuit for A equals B equals C equals 1. So they're all 1, and then D is 0. So first, let's write each one of those inputs down. We know that C is 1 and D is 0. I go back to the definition of NOR. Go back to the truth table for NOR. If one input is 1 and one input is 0, the output of a NOR gate would give you a low. The only way I know that is by studying the truth table and understanding how NOR works. So as you're putting in your study time, you're going to want to make sure that you have memorized how the NOR gate works in comparison to OR. So 1 and a 0 going into a NOR gate would give me a 0. Exact opposite of what an OR gate would give me. Next, I have A and B and the 0 from before going into a NAND gate. Well, A and B are both 1. Now remember the idea with NAND. The output of a NAND is always going to be high unless all the inputs are high. So in this case, I have one input that's low, two inputs that are high. That's going to give me a high at the output. So this example really forces you to tie everything together between NAND, NOR, and implementing a circuit from an expression. And that is the three main, those are the three main topics that you should take away from this video today.